Sombra de un pez. Bella ciao, ciao. Bella ciao, ciao, ciao.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now that we talked about the dissociation constant for water, now let's talk about pH value calculations. So you guys all know that in chemistry, pH is a numeric scale used to specify the acidity or alkalinity of an aqueous solution. And it's basically the negative logarithm of the activity of the hydrogen ion. So if you look at this, the concentration of the hydronium ion, or the H plus ion, and the OH minus ion is much more convenient to write as logarithms. So now when we talk about pH, we're talking about the hydronium ion concentration, but based on a logarithm. So remember, the log of 1 is 0, and the log of 10 to the power of negative 14 is negative 14. What this means is that most solutions have a hydronium ion concentration between 1 and 1 times 10 to the power of negative 14 molarity, or moles per liter, since the pH scale goes from 0, which is acidic, to 14, which is basic. So the concentration of the hydronium ion of neutral water at 25 degrees is 1 times 10 to the power of negative 7 molarity, which we talked about previously. And so now let's try to calculate the actual pH value. pH is the negative log of the concentration of the hydronium ion. So the negative log of 1 times 10 to the power of negative 7 molar is minus 7, which is positive 7. So that's why the pH scale goes from 0 to 14, and water at a pH value of 7 is going to be neutral, right here. And so remember, before change in one pH unit, the concentration of the hydronium ion changes by 10 due to the logarithmic scale. So similarly, we defined POH as the negative log of the hydroxide ion, OH minus. So the exact same equation as the hydronium ion that was for pH. And so since the ionization constant for water, Kw, is the concentration of H3O plus and OH minus, as we saw before, and this was 1 times 10 to the power of negative 14, we can calculate this different equation. So let's talk about a rule for logarithms. If you have the log of A multiplied by B, this can be rewritten as the log of A plus the log of B. So the pKw is the negative log of Kw, so kind of like pH being the hydronium ion concentration, pKw is the negative log of the ionization constant Kw. And this is equal to the negative log of H3O plus the negative log of OH minus. The reason why we were able to get this is because Kw is multiplying the hydronium ion concentration with the hydroxide ion concentration, And when you have the log of A times B, you can rewrite it as the log of A plus the log of B, and that's what we did, the negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration. So now we can write this as pKw is pH plus pOH. Since negative log of hydronium ion is pH, and the negative log of the hydroxide ion is pOH. So basically, pKw is now putting the ionization constant on the logarithmic scale and making calculations involving pH and pOH a lot easier. And this has a value of 14 when you add pH and pOH. So let me show you an example of how this is useful, and that'll probably give you a better idea of the point of this calculation that I just showed you. So if you know a concentration of a strong base or acid, you can calculate the pH or the pOH of it. And so as an example, we have 0.003 molar concentration of barium hydroxide, which is a strong base, and this gives 0.0060 molar concentration of OH minus ions. So what if someone asked you, what's the pH at which this is occurring? Well, since we're talking about a strong base being dissociated into hydroxide ions, we're going to use pOH. pOH is the negative log of the hydroxide concentration, and that's a value that's given to us. So it's the negative log of 0.0060 molar, and that's a value of 2.22. Now, since we know that the sum of the pH and the pOH has to equal 14, remember, because pKw is the negative log of Kw, which had a value of 1 times 10 to the power of negative 14. So the pH is going to just equal 14 minus 2.22, which is 11.78. So as you can see, this relationship between pH, pOH, pKw, and Kw will allow you to do a lot of different calculations based upon the information that's given to you. So in the other case, that this was a strong acid, then you would have just been able to do pH equals negative log H plus concentration and gotten the pH value. But given an acidic solution, and if someone asks you what's the pOH of that, again, you can use this equation where the pH plus pOH must always equal 14.